under Royal Study Fellow at University of Cambridge. But I want to give a brief introduction on my research interest. So if someone, if you are interested in my research, we can have a chat and to see if there's opportunity to collaborate in the future. Actually, most of my research work developed based on solid and computational mechanics together with the assistance of machine learning. And I'm interested in to develop the phenomenological model and micromechanics as the model to describe and investigate the social behavior. In terms of application, I care about the multi-scale and multi-fidelity modeling programs, and I also did a lot of work about the in-scale and the remote monitoring work. And recently, I'm interested in to develop applying information-based data-driven modeling. I want to show some examples on my research work. About the in-scale modeling and risk prediction, and this research work I did during my 3 years master study. I care about the tunnel-ground interaction. We just installed a lot of sensors inside the tunnel, the wheel as a grounder to monitor the tunnel-grounder interaction. And personally, we want to use advanced FEM modeling to analyze this interaction, but actually it is not realistically in practice if we want to use advanced FEM to achieve the real-time monitoring prediction, because the field work won't wait for you to complete all this work to do some prediction and monitoring. So we can because of this reason I transfer my research interest to the data-driven modeling. We collect a lot of data about the geological information and also the shared machine operational parameters, as well as the tunnel geometric information such as diameter. We just built a very large database and train the data-driven model to predict the real-time ground tunnel responses. And then the predicted response, ground response, can be used to regulate the operational parameters of shared machine to control the risk. So after my master study, I realized it actually is very important to understand the behaviors and properties of soils if we want to go into this engineering skill program. So I also focus on the data-driven modeling methodology. I developed, as we know that many machine learning algorithms were proposed by the computer science domain. So actually, there is a problem. Some of these algorithms may be perform very well in their domain, but for some programs in our domain, this algorithm may be not very suitable. So in terms of the methodology, I just modify this algorithm to make them adapt to the programs in our domain. I won't go into many details. Just if you are interested, you can just read the paper. Some of machine learning algorithm is to make the model more reusable and adapt to some sparse data and considering uncertainty. And after use this, after propose this methodology, we can just use this algorithm to describe soil behavior such as anisotropy, path-dependent, and rate-dependent, and then we can just encode this data-driven model into the FEM numeric modeling to model the engineering skill program. And this part is about my great science project. If I care about the micro mechanics. Here is the view of this project. It's about reconstruct of particles from granular machine from their CT imager, and then just put these particles to the DM modeling to model their mechanical behavior. But what I want to do is to use data-driven. You can see that there is a larger path, and it's totally based on data-driven modeling. What I want to do is to just because we have got the CT imager, we can extract their particle scale information, and then we can input their particle scale information to the data-driven model to directly predict their mechanical behavior, and then we can compare it with the effective value. They can be made by experiments or DM modeling. This is if we can do that, actually it's very easy to complete the kind of method to describe a soil behavior. We just need the city image of the soil sample, and then we can use the segmentation and representation algorithm to get the hyperspace information, and using the data-driven algorithm, and then again use data-driven algorithm to get their macro scale behavior, as well as there are some hyperscale information such as the public information. So let's go back to today's topic. The representation consists of 6 parts. Firstly, I guess everyone is very familiar with soils. It's a natural material. We can see that every day, every year. And actually, soils are also the very commonly used construction material, such as clay. They have various scales from millimeters such as to centimeters, like we said, to even larger such as the rocks. And generally, we can just make some samples, which sometimes we can call it the representative element of volume REV, and to do some mechanical tests in the laboratory, and then we can understand their properties and behavior. Because we know that many engineering programs and HRMs are directly related to their mechanical behavior, such as the Kansas Airport. If I remember correctly, the settlement of this airport now is over 10 meters, and the title of Kita Tower is a very typical example in our domain of the Devil's Flow and sinkhole. All these things are directly related to the mechanical behavior of soil. And how to describe the soil behavior when research branching to develop a phenomenological model. There are various theoretical frameworks such as elastic, incrementally nonlinear, elastoplastic, and micromechanical. We don't need to know details of these models. We can just think they are mathematical equations. We just want to use these equations to describe the nonlinear behavior of soils. Based on this model, we can just integrate this model with FEM modeling to model some engineering stuff around the pile, foundation, slope, and dike. And also there is another research branch to describe soil behavior called discrete element modeling. In this framework, actually, they just each soil particle is regarded as a virtual particle in the simulation, and the best idea is to describe the interaction among all particles, and we can get their velocity and force just based on different laws. So some people may think this kind of way is more natural, but the problem is that the computation cost is very large for this kind of method. You cannot count the number of particles even in a very small soil sample. So it will be a problem if you want to model some engineering scale problem. And so I just give a brief summary of kind of method of modeling soil behavior. And this is about the development of phenomenological model. We know that these models have fixed their experience with some prime assumptions, and to describe the complex soil behavior, now the model is increasingly complex, and increased model and state parameters are incorporated in these models. So the problem is that when we integrate these models with FEM models, non-convergence will be a problem, and also the computation cost will be large. And also there are various methods developed based on EM, such as multi-scale modeling, but also just like I said before, the computation cost is a problem. So this is the motivation why I transfer to consider machine learning associated modeling. Actually, this machine learning is called by a system neural net, but it's formally defined by Tom Mitchell. This machine learning is a study algorithm that improve their performance of some tasks with past experience. Based on this conception, how to use this algorithm to describe soil behavior, we can, the concept is very simple. We just use history, string information, and the kind of increment as the input to predict the kind of space. So based on this framework, we don't need any prime assumptions, and it's also very easy to implement. And also because it's just a direct input output mapping, so the computation cost wouldn't be very much. But there are also some limitations of kind of data-driven modeling. The first thing is that we need to a lot of high-quality data. It may be not a problem in other domain, but it would be a problem if we care about the mechanical behavior. If you do some mechanical tests in the laboratory, you would know it actually is very tedious and time-consuming, and it's not realistic to do a lot of experimental tests just to acquire some data. And if we do like this, actually we cannot identify the advantage of data-driven model, right? With this sufficient number of data, we can use the conventional consuming model to describe their behavior. And the other thing that about the model, many people criticize the data-driven model just like a black box, because the model, we don't know what happened inside the model. We just give some input output, right? And the last thing is about output. Just like I said, as long as you give the input, the data-driven model can always give you output, but we don't know the reliability of this output, right? So based on these programs, I just proposed three methods to overcome this limitation. And also this is the main topic of my today's presentation. I will introduce them later. So the next part is about the data-driven modeling of complex test-dependent social behavior. As we know, the conventional neural network is just redirect input to output information. But there is actually for the test-dependent social behavior, there is a problem that the kind of space stream response actually reflected by the previous stream history. Because of this reason, this conventional neural network may not work to consider this factor. So we just resort to an algorithm called non-short-term memory neural network. The main characteristic of this algorithm is that its kind of hidden information is affected by the previous hidden information. So this characteristic complies with the characteristic of the test-driven social behavior. So we just use the algorithm to describe social behavior. And now just like the conventional constitutive model, the input parameters of the data-driven model also include the physical properties. Here, example, such as initial void ratio is the physical property, and the state parameters include the static state parameter, which means their values keep the same during the whole process, such as the confined pressure and the strain increment, and the other is the dynamic state parameter, which means the change, such as the strain value. But here we still the previously predicted output of another type of input parameters, because we want to use this filter information and to predict the kind of information, which is actually very important for the if we want to describe the test-dependent social behavior. So finally, we just need the feedback training plus LSTM to model test-dependent social behavior. And here is an example about the proposed method to predict the behavior of Pascal set, and here is a comparison among different algorithms. We can see that LSTM obviously outperform other algorithms to capture the strain relationship. And you can see that particularly in the initial area, our algorithm actually cannot capture the exact mechanical behavior. And also, we applied to model a more complex case about cyclic loading. We can see that actually we can identify some errors in this area, but actually this kind of result is acceptable in our domain. Because so a cyclic behavior actually very complex. Even for many people have preoccupied with developing conventional customer model describe this cyclic behavior, but there still are some difference between the static value and the predictions. But we can see that the main characteristic can still be captured by the data-driven model, such as the cycle mobility and also the detection. So the previous model I talked about actually were totally developed based on existing database, but actually we don't know what will happen if the performance of the model on the data that is totally outside the database. This is a problem. So we just impose some prior information to the neural network to constrain their predictions. Here is an example about the hyper-elastic model. So sorry for many equations. Actually, this model can be used to describe the rubber and also the elastic behavior of soil. The key of this kind of model is that it has a potential function, and because based on this potential function, the strength and strain, the strength and strain have to be constrained by this relation, and so based on this information, we can just import them to the conventional neural network. Here is just a framework. We just use the history, energy, and history potential and strain components and the strain increment as the input to predict the current potential. And this part actually is total from the conventional neural network, right? From input to output mapping, but there are two additional outputs. These two outputs are derived from the existing knowledge from the hyper-elastic model. So now the training process is to reduce the nodes on these three nodes terms, rather than only one term in conventional neural network. So based on this framework, actually the conservation of energy can be constrained in this framework. So here we just generate some synthetic data based on the hyper-elastic model, and we generated 100 modeling passes and 20 for training and remaining for testing. And also here note that there are ensemble and downsample data set, which means that the strain increment, the magnitude actually is the same with the raw data, but the difference is that the strain increment is different. This one, the red one means that the strain increment only a half value of the raw data, but the blue one means that the strain increment double the value in the raw data. Here is the change of loss value during the training process. We can see that the loss can converge after about 10,000 echoes, and we from the blue one we can see that blue one shows whether the prediction of the neural network now satisfies the conservation of energy as I indicated before. We can see that this node value can also converge at a very small value. So here is the result on testing that we can see that on the raw data, both PiNet and MRNN show great agreement with the desired value. But for the ensampling and downsampling data, MRNN actually cannot capture the real mechanical response because we know that in these two data sets, the strain increment is totally different from the original training data. So, but with the context of the prior information, we can see that the PiNet can still capture the the mechanical behavior of the on the new tether. So this result actually shows the PiNet in modular response on the unknown data. Okay, so if we here is another problem about the number of data and I introduced before for the mechanical behavior of soil samples. If we do not get enough number of data, how to develop a robust data model? We just propose a multi-fidelity with the neural for MRNN. The best idea is that we personally just use some synthetic data generated by a random conventional considered model with random and model parameters to generate a lot of data, and then we have a delivery model to train on this data. The aim is just to identify the outlying rough but correct prime information. So if we input the data of soils of interest to the neural network, of course there will be a difference between the prediction neural network and the expected value. But it's okay because we have a hybrid model to capture this difference. So finally, to sum the prediction of locally model and hybrid model, we can get the right response of the soils of interest. Here, I also use the linear regression to just refine the final prediction. So based on this framework, we can live with the sparse hybrid data and also the existing knowledge. And here example, we just use a critical step as a model to create the locally data with the initial word vector equals to 0.7. And the various loading passes are generated with different unloading points. We can see that the model can be retrained, and also here we used a virtually experiment data, which means that the hybrid data is also generated by this model, but the initial word vector is different. We just use two loading passes data to calibrate the hybrid model. We can say that the model can be well calibrated, and the remaining and loading passes data are used to test the model. Here we can see that actually the prediction of locally model is totally different from the expected value, but after calibrating by the hybrid model, the prediction can be consistent with the expected value. I also compare the effect of the number of hybrid model on the hybrid data on the model performance. As expected, with the increased number of hybrid data, the accuracy model can be improved. And also, I did a interesting, which I think is interesting, about the use conventional neural network to train a data-driven model based on the mixture locality and hybrid data. And now we can see that actually the area is very large. The only difference in this case is that we do not use MRNN framework. We can see that the prediction just like this is reasonable because we know that compared with the number of hybrid data, actually the number of local data is very larger. So the training of for this kind of direct one-shot training it just aims to reduce the error on the not on the local data because they just dominate in the core database, right? But with the MRNN, we can see that with only very limited hybrid data, its prediction can be calibrated to the right value. And also, I applied the proposed framework to the experiment data. Nobody data just generated based on very physical capacity model, and the hybrid data were from Hong Kong marine deposit experiments. We can see that just with limited number of hybrid data, the training data, the prediction of the remaining loading passes can show great agreement with the exact value. And also, I compared MRNN and the PiNet as the no-predictive model under the MRNN framework. We can see that with the PiNet as the no-predictive model, actually the final prediction accuracy of MRNN can be improved, particularly in the initial area. And also for the cyclic loading, we can also see that with the PiNet as the no-predictive model, the prediction of the cyclic behavior is much better than the MRNN with the NN as the no-predictive model. Here is something about uncertainty quantification, because we know that soils are characterized by uncertainty, and also data-driven modeling also has a lot of uncertainties. Even for the same data set and the same algorithm, different people can get a different model. So to quantify this uncertainty, I think it's necessary to incorporate uncertainty into the previous proposed data-driven framework. Here are three methods to incorporate uncertainty into the data-driven model. One is Bayesian inference. It's a theoretical method, but it's not realistic to define the neural network, because we know there are not a number of ways and basis and neural network. If not, the computation cost will be very large if we want to use Bayesian inference. And another method is approach Bayesian inference, and the next one is ensemble learning. Here I just use Monte Carlo data to incorporate the uncertainty into the data model. This method actually is very simple. We at each during the testing process, the number of collections, there is a fixed probability of the number of collections between neurons are randomly cut. So if we compute 10 times, we will get different. We'll get 10 different architectural neural network. Of course, we will get 10 different results, and finally we can get the mean value and the standard deviation of this prediction. And here is just an example. We can see that now the prediction of data-driven model can be wrapped with a confidence interval, which is actually useful for an engineering design. We care about the reliability of the prediction. So after the develop these data-driven models, the final thing is to apply these models in engineering practice. So I just encode the model into conventional FEM framework. Most part actually are the same with the conventional FEM modeling, from displacement interpretation to displacement to brain convention. The only difference is that the strength update vertical adoption points, because now we use that driven model to update the strengths at the golden point, and then we just iterate this whole process until the whole system achieve to equilibrium. And here just give some examples about animal tests. We apply the data-driven FEM on loading, on unloading, reloading, and also proportional loading process. We can see that we compare with MCC model modified campaign. Actually, we can see that the data-driven FEM actually show very stable results upright, and also the predictions are consistent with the FEM with the MCC model. And here is example about the strain optimization, which is achieved by a weak element. And we apply the two different loading phases. One is monotonic, one is periodic. And here we can just extract the contour of the degree tolerance strain. We can see that the location of the shear band and also the signs are actually roughly the same with the impact band. We also extracted the strength relationship at point B, which is the Gaussian point inside the gamut. To see that the mechanical response also comply with the back event. The positive result shows the possibility of integrating data-driven model into FEM to model engineering scale program. And finally, I also developed a GUI for people to reproduce the results I showed before. And the program was based on testing flow. And now it's attracted over 3,000 readers. And it's actually it's not very advanced, but I think it's very useful. Otherwise, if you don't want to have so many people to read it, and you can just use this UI to develop your own data-driven model, and also there are various algorithms you can select, and also you can use your trained model on the new data that you are interested, and do some parametric stuff. And here are just some concluding remarks. The feedback modeling with prime information-based and neural network can accurately reproduce complex continuous behavior, and multi-fidelity residual network provides a potential way to develop a robust data-driven model with fast data. And data-driven model can be embedded in LSTM code for modeling boundary embedding programs. And also, thanks for all collaborators. That's all. Thank you.